class. Today we're going to talk about Chapter 2.2 in mixtures. We have an example here of a coffee cup with coffee in it, and we know that coffee is brewed by mixing the hot water and the coffee grounds in the beans. But what does that mean as far as a mixture is concerned? So we're going to look at the components of understanding the different types of mixtures. The important thing is to understand it at a macroscopic level and a submicroscopic level. So hopefully with the examples I show you, you'll start to understand those differences. How can mixtures be classified? Well, if you take a salad bar, for example, you have different types of vegetables in the salad bar, and you as a customer can choose however many tomatoes you want, cucumbers, whatever. And so each salad mixture has different types and amounts of components. So when we look at a mixture, it's a physical blend of two or more components. So what kind of mixture would a salad from a salad bar be? Hopefully you'll understand it by the classification of the two kinds of mixtures. Most samples of matter are mixtures. Some mixtures are easy to recognize than others. You can easily recognize chicken noodle soup as a mixture of chicken, noodles, and the broth. But recognizing air as a mixture of gases is more difficult because you can't see it, and we have several components to that air mixture. Also, the fact that air can be drier or more humid shows that the amount of one component of air or the water vapor can vary. Based on the distribution of their components, mixtures can be classified in two ways. Heterogeneous mixtures, right here, and homogeneous mixtures. I know you've heard these in the past, and I just want to clarify them for you so it brings back some recollection. Plus, by now you should have written out your 2.2 process journal and really read over the material. For example, heterogeneous mixtures is that chicken noodle soup I was talking about, and those noodles and the things in the broth are not distributed equally or evenly throughout the mixture. There's likely to be different amounts of chicken and noodles in each spoonful you get. So that would be classifying it as a heterogeneous mixture. When we look at a homogeneous mixture, such as olive oil, that substance has several components, but it's distributed throughout it evenly. So olive oil doesn't look like a mixture, in which case we actually call that a solution. The same is true with vinegar. Vinegar is a mixture of water when we talk about homogeneous, water and acetic acid, which dissolves in water. So here are two examples of homogeneous mixtures, and that is a mixture in which the composition is uniform throughout. Another name for homogeneous mixture is the solution. So that's what I was speaking about earlier when I first introduced it. Many solutions are liquids, but some can be gases like air or the gases on the periodic table. As we learn to combine them, you'll start to understand that homogeneous uniformity throughout, because the way gases work, which we discussed in 2.1. Some are solids, like stainless steel, and they have a mixture of iron, chromium, and nickel to make the stainless steel. Okay, so when we talk about homogeneous mixtures, the term phase is used to describe any part of a sample with uniform composition and properties. By definition, a homogeneous mixture consists of a single phase, meaning that's uniformity throughout, and where that salad bar chicken noodle soup mixture is not. So that wouldn't be a single phase, there would be several phases depending on what it is. So a heterogeneous mixture, a perfect example would be to mix our oil and vinegar, and you would have an oil phase which floats on the water or the vinegar phase. So when oil and vinegar mix, they are a heterogeneous mixture, and you can see here the phase difference. So the oil is sitting on top of that vinegar right here, or if you used water. So the water or the vinegar would sink, it would be more dense in the material, and this oil would be less dense and would sit on top as a double layer or two phases. This would be the first one, this would be the second one. Okay. At the beach, you realize that both ocean water and sand are mixtures, which is a homogeneous mixture solution and which is a heterogeneous mixture. What do you think it is? Salt water is homogeneous and sand is heterogeneous. It's pretty, obvious. So think about that when you're thinking about the types of mixtures. How can mixtures be separated? If you have a salad containing an ingredient you don't like, you can remove it with a fork. That's easy. Many mixtures are not as easy to separate, especially when you're looking at the submicroscopic world. But for the obvious things, you would separate a mixture of olive oil and vinegar by decanting them and pouring off the oil layer first. A lot of times you would use a spoon upside down as you pour the liquid over the spoon so that you could help decant that. You might cool the mixture until the oil turned solid, and then you'd have, this solid mass that you could just remove completely from the other phase, like the vinegar or water. To separate a mixture of olive oil, you could also freeze it, where you can see where the olive oil would congeal, and again it would be a separate layer and you can remove it all together. Differences in physical properties can be used to separate mixtures. So back to the coffee filtration. At the right, you can separate ground coffee beans from brewed coffee. The liquid brewed coffee passes through the paper filter, but the solid coffee grounds cannot pass through the filter. So one thing thinking about separation of mixtures would be filtration. Filter paper used in a laboratory is similar to coffee filters. Filter paper is often placed in a funnel, then the mixture is poured into the funnel. Solid particles that cannot pass through the filter remain in the funnel, and the rest of the particles pass through. So, like for example, in geology, you could separate out certain rock levels, rock sizes, by using mesh and allowing sand to fall through, and then you would hold on to the larger rocks in the filter or the mesh. The process that separates a solid from a liquid in a heterogeneous mixture is called filtration. So, the coffee. Brewed coffee is a mixture of ground coffee beans and water. What process is used to separate ground coffee beans from brewed coffee? And I think the answer is pretty obvious. Filtration is used to separate it. Now, Distillation. Tap water is a homogeneous mixture of water and substances that are dissolved in the water. One way to separate water from the other components in tap water is through a process called distillation. And you have probably looked at this and maybe even drew this in your 2.2 process journal. During a distillation, a liquid is boiled to produce a vapor that is then condensed into a liquid. And therefore, if you look at this example of a small-scale distillation, you can see this apparatus and the way it works. So you have your Bunsen burner, heats up your tap water, this is your mixture, and the steam, you can record, we all know the boiling point of water, 100 degrees Celsius, and so the steam comes through this tube, and then the cold water can come out through here or pass through in this way and out this way. And the condenser allows the purified water, in other words, like none of the minerals that may have been in the tap water, they're gone, and the distilled water is left. So it's totally cleaned water. It's not too flavorful. It's not recommended to be a nutritious liquid, but it's great for experiments. So as water in the distillation flask is heated, water vapor rises in the flask and passes into a glass tube in the condenser. The tube is surrounded by cold water, which cools the vapor to a temperature at which it turns back into a liquid. So that steam process occurs in here as it's going through the tube. The solid substances that were dissolved in the water remain in the distillation flask. This is because their boiling points are much higher than the boiling point of water. So you may see little solidified pieces, usually of calcium, magnesium, in the flask, the leftover, dissolved water after it's all gone. All right. How could a mixture of aluminum nails and iron nails be separated? Think about it. In order to identify how to separate aluminum and iron nails, the properties of both aluminum and iron must be known. Okay, so the properties are this. They're both metals. They're gray color. Aluminum and iron do not dissolve in water, but the difference is aluminum is not attracted to a magnet and iron is. So that's an obvious way to separate out a mixture of these two things. So you have to think about this as a scientist, identify a property that can be used to separate different substances from each other. And so that would be an obvious one for aluminum and iron. Iron would be attracted to a magnet, aluminum would not. Which physical property does filtration rely on to separate mixtures, and which does distillation rely on? Filtration relies on the size of a particle or a molecule of a substance. Distillation relies on the boiling point of the substance. So that's important to think about in experimentation. Okay, so the key concepts. Mixtures can be classified as heterogeneous mixtures or as homogeneous mixtures based on the distribution of their components. The differences in physical properties can be used to separate mixtures. And then your terms are as follows, which you have seen in your book. The end. Hope you enjoyed.